The shocking truth about equilibrium stages. Are you doing it wrong? Part 3 is an episode of the Degrees of Freedom project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage linked in the description. This set of 3 videos, The Shocking Truth About Equilibrium Stages, Are You Doing It Wrong? Parts 1, 2, and 3 explain the mass balance equations for a single stage in separator and provide 3 examples. Separation equipment is extremely common in the chemical process industry, and most of these separators have multiple stages. The overall split fractions for the separators are calculated by chaining together the calculations for the individual stages. The full calculations require both mass balances and energy balances, but the full calculations will have to wait for us to cover the first law of thermodynamics. These videos only describe the mass balances. The third example is a liquid extraction stage with a 2-liquid equilibrium using a ternary phase diagram. You will note that we've relabeled the inlet and outlet flows with L1, L2, L3, and L4 instead of liquid and vapor. That is because we have 2 liquid phases coming in and 2 liquid phases exiting. The problem statement reads, an equilibrium stage in the liquid extraction process has an equal molar feed of 50% water and 50% acetic acid and a flow rate of 180 mol per minute. This feed needs to have most of the water removed. To this end, the other feed is 100% chloroform at 120 mol per minute. The stage is operating at 298 kelvins and 1 atm. Determine the flow rates and compositions of the product streams. How well does the first stage remove the water? The water, acetic acid, chloroform ternary phase diagram is given below. We begin with the overall mole balance. The total molar flow rate is the sum of the molar flow rates of the 2 input streams, or 300 mol per minute. The molar flow rate of each species in each input stream is a product of the mole fraction and the input stream total molar flow rate for each of the acetic acid, chloroform, and water. The overall mole fraction of each species is the sum of the molar flow rates of each species in both input streams divided by the total molar flow rate. Plugging in the known compositions yields the overall composition of acetic acid is 30%, the overall composition of chloroform is 40%, and the overall composition of water is 30%. Since we know the temperature, pressure, and overall compositions, we need to do a flash calculation. Since we're using a phase diagram, the fraction of the exiting streams, that is liquid 3, is the overall mole fraction of species I minus its mole fraction of species I in liquid 4 divided by the mole fractions of species I in liquid 3 minus the mole fraction of species I in liquid 4. If we had perfect accuracy in reading our phase diagram, we could use any of our 3 species for the calculation. But since we don't, it's best to use one that has the widest spread of values to make the differences as large as possible to minimize the effect of the inaccuracies. In the spreadsheet, we calculated and averaged all 3. Better still would be to calculate the length of the line segments in 2 space, but I'm not about to convert the ternary coordinates to Cartesian xy coordinates and then calculate the lengths. To perform the calculations, we need the mole fractions in each of the 2 exiting phases, which you'll get from the phase diagram. Here's the ternary phase diagram. We'll begin by marking the 30% acetic acid, 40% chloroform, 30% water point. We'll then draw the tie line, which is fortunately on top of one of the existing tie lines. If the overall composition were between the existing tie lines, we will draw a tie line that went through the overall composition point and had a slope intermediate between the 2 existing tie lines. First, we mark and read off the composition of the water-rich phase, phase 3 or liquid 3, which is 32.6% acetic acid, 1% chloroform, and 66.4% water. Finally, we mark and read off the composition of the chloroform-rich phase, phase 4 or liquid 4, which is 28.1% acetic acid, 69.6% chloroform, and 2.3% water. In the ancient days, students were required to purchase engineering rules, which were used to increase the accuracy of reading phase and other diagrams. These days, if you actually need high accuracy in reading an engineering diagram like a phase diagram, use pixel counts on a digitized image. Practicing engineers use software like DWSim that will do liquid phase equilibria calculations. Anyway, with our calculated overall compositions and our compositions for liquid 3 and liquid 4 read off the phase diagram, we are ready to calculate the fraction of liquid 3 exiting. It comes out to 43.1%. By difference from 1, the fraction of liquid 4 exiting is 56.9%. We can then calculate the exiting flow rate of liquid 3 as L3 times n.toad, or 129 mole per minute. And by difference, or by L4 times n.toad, the exiting flow rate of liquid 4 is 171 mole per minute. Here's a screenshot of the spreadsheet of the results. As usual, the original of the spreadsheet is linked on the website. The given problem parameters are in green. The answers are bolded. Here for comparison is a DWSim PFD and the result from running the simulation in DWSim. It used the same thermodynamic method, modified UNIVAC, NIST, as was used to generate the ternary diagram. The difference between the DWSim answers and the answers from reading the ternary phase diagrams gives you a feel of how much error there is when doing a careful reading of the phase diagram. The phase diagram version of n.L3 is about 0.5% higher than the DWSim version. The phase diagram version of the n.L4 is about 0.35% lower than the DWSim version. The mole fractions show about the same degree of error. Again, in professional practice, something like DWSim is more accurate and likely easier to use unless the only data you have are from a printed ternary phase diagram. The takeaways for this video are: 1. Liquid extractions works very similarly to distillation stages and other equilibrium separation stages. 2. The biggest challenge is getting and using the phase equilibrium data. 3. Using chemical process flowsheet software such as DWSim removes most of the tedium from the process if you know what you're doing. Thanks for watching. This video was brought to you by the DOFPro team.